Hello and good morning everyone. Welcome you all for the NPTEL online course on economic operation and control of power systems. In today's class we'll learn about economic dispatch problem using dynamic programming approach. In the last class we have learned about the classical methods. To start with the lambda iteration method. Lambda iteration method, we initialize the lambda value, and for that specific lambda value we identified what is the generation, because lambda is nothing but df by dp. So we could able to get the generation of each generators and then check whether the sum of the generation is equal to demand or not. If that is and for that calculated generations, if it is matching the demand, then that is the optimal lambda. Otherwise, if the generation is higher than the load demand, then you have to decrease the lambda. On the other hand, if demand is higher than the generation for the calculated generated values, then you need to increase the lambda. So you need to project the lambda, right? First, for the first iteration you have taken some lambda, then you increase the lambda, let's say by 5% or 10%, then you project the lambda. Projecting the lambda is done with respect to the change in error, because you have two different values already earlier with the two iterations, whatever value you have got, the lambda and the error. So change in the error, how much is the change in the lambda? So based on that you project the lambda, then once you project the lambda, then you increase the lambda again. For the calculated lambda you obtain the generation. You go on with the same iteration unless and until you meet total generation is equal to total load. So then we went on to the gradient method, because in certain cases where you have complications in terms of the expressions, polynomial expressions, like there is a fractional degree and other things. So the lambda iteration is quite difficult. So we went to gradient search method. In the gradient search method, the objective is to find the maximum descent, right? So the maximum descent is found out with respect to each variable. Let's say there are n generators, then there will be n plus 1 variable, right? So you obtain the gradient function. For the gradient function in this case is the gradient of the Lagrangian function, right? Such that there is a tolerance limit decided and each variable will be converging closer to its value, which is 0. It means df by dp minus lambda should be is equal to 0, as close as possible to 0. So then you will converge. There will be some tolerance limit that you fix, based on that it will converge. And then but sometimes choosing lambda in the case of lambda iteration method or gradient search method also have some limitations. So what we go for modified method, right? Modified search method, and then we make a variable as a dependent on other variables, and then so that we can have a better convergence. So and the best approach is, we identified it's a Newton's method, where we could able to exactly find out that correction factor, and with that correction factor we could able to converge in a very quicker manner, right? Now in today's class we will discuss about the dynamic programming based approach. Before that, let me give you an analogy of investment plans, how best you can get the profit by investing in different ventures, so that we can use the same aspect, same analysis to the power system problem, right? So it's we call it as forward recursion algorithm. There are two types of dynamic programming, forward recursion and backward recursion algorithm. So let's take forward recursion algorithm. So in this you can see here there are 4 different ventures, 4 different companies where a person is ready to invest, right? And the investment amount could range from 0 unit to 10 unit. This could be, no, it's just a per unit value. You are very familiar with per unit, right? Similar to that, the year it could be $1, or you can consider to be 1 unit means $1,000 or $1 lakh. It's up to you. So now find an allocation policy with 10 units to be invested that yields the maximum profit, right? Now in this case of the table is given, where it is mentioning that if let's say you have 1 unit and you want to invest total this 1 unit into venture 1, then you will get profit of 0.28, and if you invest in venture 4 you will get a profit of 0.2. Similarly at venture 2 you will get 0.25, venture 3 you have 0.15 of profit, right? Similarly at different investment level, each venture has a different range of profits that is offering to the investor. and it is not linearly increasing or decreasing, it's a random value that is coming up. For example, if you see here, sometimes the investor is investing at venture 1, if he is investing, let's say 2 unit, then he is getting 0.45, and reasonably if you think if he is investing 10 unit for the venture 1, he should get 0.28 into 5, right, if you do the mathematics, but that is not the case here. 0.28 into 5 should be 1.4, but he is getting 1.38. So you cannot use the simple mathematics to have this analysis. So this profit varies over the investment and across the different ventures also. Now this is the table. Now given a limited amount of money to allocate, the problem is to find the optimal investment allocation. That means if I have 10 units to invest, whether is it worthy to invest just all the 10 units in venture 1, or can I invest, let's say 4 units in venture 1, 3 2 2 units in venture 3, 0 units in venture 4, whatever. So what is that combination of investment in different ventures for a specific amount of investment that an investor is interested to do? What is the best combination? So that's what we are interested to find out now. So now let x1, x2, x3, x4 be investments in for stage 1 through stage 4, right? So that means the profit of investment in x1 is Vx1. The profit once one obtains in investing the venture x2 is Vx2, similarly Vx3 and Vx4. These are the profits. So x1 plus x2 plus x3 plus x4 is equal to 10, that is a constraint, right? Maximum investment that can be done is 10 unit. Now to transform this into a multi-stage problem, let the stages be x1, u1, u2 and a. So if you remember dynamic programming, we divide a problem into different stages, right? And in each stage you have different states. In each stage you have different states or nodes, and there is a policy, right? So we are finding suboptimal policies to reach out to the ultimate policy, right? So now the stage 1 we call it as u1. So where u1 is nothing but x1 plus x2, investment across venture x1 and investment at venture x2, and the condition is u1 should be less than or equal to a is the ultimate destination, that means the total investment, right? Obviously investment of 1 and 2 will be less than investment of 1 plus 2 plus 3 plus 4, right? And then u2 is that the next level, next stage, that includes the investment at the previous stage, which is x1 plus x2 plus investment at the third stage, which is x3. So u1 plus x3 will give you u2, and ultimately a is nothing but u2 plus x4, right? Now the total profit is the summation of the cost or the profit obtained with respect to the individual investment, right? Now which can also be written as v1 x1 plus v2 of u1 minus x1. u1 is x1 plus x2, that means x2 is u1 minus x1. Similarly you express with respect to the different stages, and at the second stage we can compute f2 of u1 is equal to maximum. Let's say you're calculating at stage 2 where there is only 2 investment which is considering, right? So that is x1 and x2. So we are finding the maximum profit at the stage 2 is the maximum profit that one can get with the investment across both the ventures v1, x1 and x2, right? Now let's try to understand with this problem. So x1 or x2 or u1, it is varying from 0 to 10. The profit one gets is v1 of x1 by investing at x1 and v2 of x2 which is investing at x2, and f2 of u1 is the maximum of v1 of x1 or v2 of x2, right? Then we will see if the investment is 0, then you will get 0, 0 investment. If let's say the investment is 1 unit, then v1 of x1 suggests is 0.28 and v2 of x2 suggests it is 0.25, right? 0.28 and 0.25. So if let's say you have just 1 unit to invest, so it's common sense that you invest totally in v1 x1, that is x1, and that is coming out to be 1, 0 combination. This suggests if you have 1 unit, you invest completely on x1 and 0 at x2. Let's say you have 2 units to invest, then the possible combination is you completely invest 2 units in venture x1, or total 2 units in venture x2, or 1 each in x1 comma x2, right. Now if you invest total 2 units in x2 only, then what you will get 0.41, that is what the table is indicating. And if you invest total 2 in x1, then you will get 0.45. But let us say you invest in x1 and x2, then what it is coming out to be 0.53. So which is the best among them? Investing on x1 and x2, because that is coming out to be 0.53. So that is what we are considering here. You invest on one unit can be invested on x1 and another unit can be invested on x2. Let us take another example. Let us say you have 3 units to invest. You have got 3 units to invest. Now possible combination are, let us say I will invest total 3 in x1 and total 3 units in x2, right. Or let us say 1, 2, that is x1, x2, or 2, 1, 2, 1, which is x1, x2, correct. Let us try to see these combinations first. If you invest totally on x1, you will get how much? 0.65. Total 3 units are invested on x2, you will just get 0.55 profit. Let us say 1, 2 combination. That means you are investing 1 on unit on venture x1, that is 0.28, plus 2 units on x2, which is 0.41. How much it is coming? 0.69. Let us say you invest 2 unit on x1 and remaining 1 unit on x2, then how much you get? 0.45 plus 0.25. How much it is coming? 0.7. So among them, which is the best combination? Maximum profit you want, right? You do not want to have minimum profit. So you want to have a maximum profit as from the investor point of view. So you will get 0.7 as the best value. So the combination is 2, 1. Like that you exercise for all different units of investment across x1 and x2. Then you will get optimal sub-policies at this specific stage for the investment in x1 and x2, and this combination is given here, right. Now moving forward, let's move on to the next stage. Now again you have this investment 0 to 10, and from the previous investment you have got the optimal cost, maximum profit you have already got, right. That is 0.28, 0.53, 0.7 up to 1.68. This is the maximum profit that you could get by just investing on x1 and x2. You just carry this table as it is. From the previous stage. Now there is one more venture which is available for you, and their profit is already been given, it's been already defined. Now let's say you start now again from the beginning. You want to invest, you have just $1 or 1 unit with you. What is the best combination to invest across x1, x2 and now x3 also, right. So with x1 and x2 you already have this value 0.28, with x3 you have 0.15, but you have just 1 unit to invest. Let's just totally depending upon investment on the best among x1 and x2, which is 0.28, correct. And what is the combination? From 1 and 2 you got 1, 0, 3 is no more relevant now, so it's just 1, 0, 0, right. And then let's take another 1 or 2 examples to have a better understanding. Let's say you have 2 units to invest, right. Now again the same philosophy you have to apply. Either you go for total 2 investments on F2 of U1, right, or total 2 investment on X3, right, or one each on F2 of U1 and X3. Let's say if you are totally investing 2 units on the best combination of X1 and X2, which we call it as F2 of U1, then what is the profit that you are going to get? 0.53, right? Now if you are totally investing on X3 venture, how much you are getting? 0.25. So which is the best again? Totally you invest on, or one each you take one each. Let's say one each means 0.28 plus 0.15. You say here this is 0.28 for one, and one if you invest 1 unit in X3 which is 0.15, totally how much you are getting? 0.4 if you invest 1, right? But what is the best? Already you have 0.53 available, which is the maximum profit that you can get. So you better invest totally on the best combination of X1 and X2. Again you will get 1, 1, 0, because in the previous case for unit 2 investment the best combination was not 2, 0 or 0, 2, it was 1, 1. That's what is given here, 1, 1, and you just retain as it is. Similarly you do it for all the investment, and you will get the optimal sub policies at stage 3 as per this entries. Now let's move on to the last stage. So in this stage, because you have 4 ventures, now you move to the next stage. In the next stage you have again same 0 to 10, right? You have 0 to 10, and you have the best combination available from the previous one, considering X1, X2 and X3 put together. Now we have a new venture to add on, which is X4. Now we will just take randomly any number. Let's say I'll take 3 here, right? I have 3 units to invest now. 3 units to invest now. Now if I have 3 units to invest, then the possible combinations could be, let's say I'll just try to figure out, let's say I'll take total 3 on the best combination of the previous one, which is F3 of U2, which is coming out to be 0.7. If I totally invest 3 on X4, which is coming out to be 0.42. Let's take another combination of 2 plus 1, right? That means 2 units from F3U2 and 1 from X4. How much it comes out to be? 0.73, right? This combination gives you 0.73, right? Or let's say you take 1 from F3 of U2 and 2 from the X4. How much it is coming out to be? 0.28 plus 0.33. How much it will come? 0.43, 0.53, 0.63, 0.61, right? This comes out to be 0.61. Earlier you have, if you totally invest on F3 of U2, it will get 0.7, or just X4 it is 0.42. 1, 2 combination, 1, 2 combination will give you 0.61, but 2, 1 combination will give you 0.73. So that is the best. So that means you invest 2 units on F3 of U2, right, and 1 unit on X4. If you consider 2 unit investment on F3 of U2, what is the best combination for 2 unit investment on F3 of U2? That is 1, 1, 1, 0, right? Then ultimately you will get X1, X2, X3, X4 as 1, 1, 0, and then a investment of 1 unit on X4, which is 1. So you will get a combination of 1, 1, 0, 1. You understand this point? Similarly you have to do it for all the investment. Let's summarize whatever we have understood, because this is very important to move forward to understand our power system problem, right? So it was not necessary to enumerate all possible solutions. Instead, an orderly stage-wise search is used, the form of which is the same at each stage. The solution is obtained not only for A is equal to 10, interestingly, but for all the complete set of values from 0 to 10. See, interest was only 10, ultimately you wanted to have this combination 4, 3, 1, 2, but in a way you get at every stage what is the best combination for every investment, for every possible investment across different ventures x1, x2, x3 and x4. Why this is important? Let's say you have invested in 4 ventures x1, x2, x3, x4 and due to some reason x4 is totally collapsed, that venture is collapsed, right? But still you have investment on x1 and x2 and x3. Now you can see what is the best combination on x1, x2, x3 itself. Then for that specific investment, for that you can easily look into the table and get the best possible combinations. For example, I will say here the total optimal policy contains only optimal sub policies. For instance, if A is equal to 10, then the best combination 4, 3, 1, 2 is the optimal policy, and for stages 1, 2 and 3, for stages 1, 2 and 3, if the x4 is gone, then considering 1, 2 and 3, what is the best investment? You get 3 units of best unit, 4, 3, 1, that is coming out to be 8 units of investment. Let us say x3 is also gone, venture is gone, then having 1 and 2 in hand, what is the best? You can go for 4, 3 investment if you have 7 units of investment to make, right? If you have just 1 unit left out, 1 venture left out, which is x1, and you have to make 4 units of investment, then best is 4, correct? So notice also that by storing the intermediate results, we could work a number of different variations of the same problem with the data already computed. Now we already computed, say 1 venture is gone, you will have other best sub policies available with you. Now we will move on to economic dispatch using dynamic programming. That means with the understanding that we have got, now we will apply the same thing in power system problem. If non-convex input output curves are to be used, we cannot use an equal incremental cost methodology since there are multiple values of megawatt output for any given value of incremental cost. Let us say you have in a specific, even in a specific generator there could be multiple valves. So you can see here the cost, the heat characteristics or cost characteristics that you get, it's not linear, it's not smooth basically, it's not smooth, it's highly non-convex problem. For non-convex problem, classical methods that we have used like gradient, lambda iteration and Newton's method have some limitations. So that holds good for gradient approach, because first derivative is what required, that you can get, but here it comes out to be like double derivative or something like that. So here obtaining a solution with the help of classical methods is little bit cumbersome. So then we go for either heuristic methods. Heuristic methods include particle swarm optimization, artificial intelligence, ANN based approaches, right? So there are so many heuristic methods available, but heuristic approaches, they go for, they search the solution actually in a given space. There could be, at some specific search you may not get an exact optimal result, you may get a better result, but it need not be a best result. So dynamic programming in such kind of scenarios can help you get a best results. So the dynamic programming solution to economic dispatch is done as an allocation problem. Using this approach, we do not calculate a single optimum set of generator megawatt outputs for a specific total load supply. Rather, we generate a set of outputs at discrete points for an entire set of load values. For all the possible load combinations, let us say from minimum to maximum, we find out the best possible generation values, right? Now let us take a problem to understand. Assume there are 3 units in the system, all are online. You have 3 generators, P1, P2, P3 are the generations from each of the generator, right? And the fuel cost associated with each of the generator is F1, F2, F3, right? Their input output characteristics are not smooth nor convex. Data are as follows. You can easily check also from here, from 50 megawatt, let us say for each generation of P1, P2, P3, where generation is varying from, we have the data from 0 to 225 megawatt of generation, right? If that means 0 generation is equal to 0, the fuel costs are not applicable. That's why we have mentioned as infinity here. It is not applicable, but that means there is no scope for operating these generations at zero value, 0 megawatt of supply. It starts with 50. So at 50, you see, for the fuel cost associated with the first generator is $810 per hour, right? For the second generator you have 750, for the third generator you have 806. That means they have different cost for each generation. And with respect, if we increase from 50 to 75, you see their variation is also non-linear. 810 to 1355 and 750 to 1155, and their proportionate variation is also different. And correspondingly, if you check from 75 to 100 also, you see they are not linear basically. It's not linear rise with respect to individual unit also. So ultimately you have the total fuel cost for each generation, right, with respect to each generator. Now let's say a problem is given where you need to identify the best possible generations for the load demand of 310 megawatt. This does not fit the data directly, right, because there is no generation value exactly equal to 310 megawatt. Either you have, any possible combination you take, the generation combination would give you either 300 megawatt or 325 megawatt, but your demand lies between 300 and 350. So we need to interpolate ultimately, right? So let's start with the help of dynamic programming. So scheduling units 1 and 2, we find the minimum cost for the function. Let's start with unit 1 and unit 2 and then take up unit 3. Now the fuel cost, or the total cost of F2 is, that means at stage 1 is 1 or stage 2, whatever you can consider. So that is the total cost involved in generation with respect to the first unit, F1 of P1. F1 of P1 is nothing but F1 of demand minus P2, right, because P1 plus P2 will be equal to demand plus total fuel cost associated with P2. So F1 of P1 plus F2 of P2 will give you total cost, right, considering just unit 1 and unit 2 over the allowable range of P2 for 100 to 350 megawatt of demand. That means let's consider just P1 and P2. What is the minimum generation that can happen combining P1 and P2? It will be 50 plus 50, right, because 50 each. This comes out to be PD is equal to 100 megawatt. What is the maximum that you can get? From P1 you get 200, right, this is the maximum above which it is not possible to generate, and for P2 you get the maximum as 150. So 200 plus 150 will give you PD maximum as 350 megawatt, right. So for the allowable range of P2 you have the demand variation from 100 to 350 megawatt. Now we need to save the cost for serving each value of demand, that is minimal and the load level on unit 2 for each demand level. Now this table will give you a better understanding. Now at first stage, we are in first stage. Now you vary the demand from 0 to 350 megawatt. Now simply you enter the data here. The actual demand will start from 100 to 350 for the combination of P1 and P2. Then the fuel cost associated for the first generator, you just put as it is, that you are getting from the previous table, from this table, right. So for the generation 1 it varies from 50 megawatt to 200 megawatt, right, minimum to maximum, and you have an individual cost which is varying from 810 rupees to $810 per hour to $2760 per hour, right. Now for this combination, now this is with respect to the generation 1. In this entry, this row, we are varying generation of generator 2 from 50 megawatt, which is the minimum generation of that particular generator, to 150 megawatt, which is the maximum generation of the generator 2, right. Now for each combination of the generator, I mean let's say let's freeze 50 megawatt. for 50 megawatt of fixed operation of the generator 2, you check what is the cost that you are getting while parallelly operating with generator 1. The cost associated with the generator 2 for generating 50 megawatt of power is $750 per hour, that you get from the table. Now to start with, from 100 to 350 megawatt, we are varying from 100 to 350 megawatt because that is the combination that you get of the demand variation from 100 to 350 megawatt. Let's say you are supposed to operate generator 2 at 50 megawatt, right, but the load is 100 megawatt. Then what is the remaining generation? 50 megawatt. Now you calculate the total cost of generation of P1, which is at 50 megawatt, and P2, which is 50 megawatt. That comes out to be 810 rupees, $810 per hour plus $750 per hour. It will come out to be 1560, right? Let's say you will go to the next demand level. The next demand level is 125 megawatt, but you are just calculating for the fixed 50 megawatt generation. Now 125 minus 50 is 75. So now 75 you have to generate by using generator 1. So what is the cost associated with the 75 megawatt of generation of generator 1, which is 1355. So 1355 plus 750 will give you the value of 2105. Now as the generator the total demand varies from 50 to the further values, right, 50 to 250, you have the data entries here, because beyond which you don't get any generator from generator 1, generation from generator 1, because 50 you have already fixed, right, 50 you have already fixed for generator 1, the maximum you get from generator 1 is 200. So 200 plus 250, 200 plus 50, 250 is the maximum value that you get with the combination of generator 1 and generator 2, beyond which even if you operate P2 at 50, there is no generation available from generator 1 to support, let us say, 275 megawatt of generation or 300 megawatt of generation. You understand this point? Now you get these values entered here. Similarly, you take the next generation capacity of generator 2, which is 75 megawatt, and the cost associated with the 75 megawatt of generation from the generator 2 is $1155 per hour. You just carry out the same iteration like we did for 50 megawatt with respect to this entry. You understand? For example, I will just take one data to help you understand. Let us say you want to operate at 250 megawatt of demand, where fixed generation of generator 2 is 75 megawatt. Now how much is the left out? Which value that I had considered? 250, right? So let us take 250 megawatt of load demand. Now we are dealing with 75 megawatt of generator 2. So remaining is 175. For 175 you check what is the value, 2427.5. So 2427.5 plus 1155, that will give you 2582.5. And what is the maximum capacity here again? If you are fixing at 75, the maximum generation available from generator 1 is 200. Now you can see, you can go to the next level here. Earlier we stopped at 250 megawatt. When we fixed the generation of generator 2 as 50 megawatt, we could only reach up to 250 megawatt of demand. Now because you have enhanced the generation capacity of generator 2 to 50 megawatt, from 50 megawatt to 75 megawatt, now you can provide an extra supply of 25 megawatt to the demand. So you can calculate up to 275 megawatt. Similarly, you keep on increasing the generation capacity from its minimum of 50 megawatt to maximum of 150 megawatt capacity, and for each combination you get a set of values, right, the set of values that is been tabulated here. Now having got these values, now you have to check what is the best possible combination of generation for each demand. Let us say at generation 50 for, let's say you are starting from 100 megawatt, right? You are starting from 100 megawatt. This is 100 megawatt. Now you have only one option available, which is generator 2 operating at 50 megawatt, and the best cost is that itself 1560, and the generation associated with that is 50 megawatt. Now you take the next step, which is 125 megawatt of load demand. Now for 125 megawatt of load demand, now you have two possible generator combination of generator 2, which is either 50 megawatt of operation or 75 megawatt of operation. Now you check which is the best. That means whether 2105 is the lowest cost or 1965 is the lowest cost. The obvious is 1965. That means if you have the load demand fixed, which is 125 megawatt, what is the best possible operation of generator 2 is 75 megawatt. Like that, let's say you have this is where you get, let's say 250 megawatt of load demand. Now 250 megawatt of load demand can be catered at 4 different combinations of generations from generator 2, which is either 50 megawatt, you can generate by using 50 megawatt of generation, or 75, or 100, or 125, or even 150 also. The 5 possible combinations are there. So among them you can check which is the lowest. So if you want to operate at 250 megawatt, if you want to supply a demand of 250 megawatt, so it is advised to operate the generator 2 at 150 megawatt, and remaining 100 megawatt is catered by generator 1. That will give the cheapest cost. So ultimately you got the best possible generation for each variation in the load demand if you have only 2 combination of generators, which is generator 1 and generator 2, right? Now that is what we have summarized here in this table. Now let us go to the next stage. Earlier you had just 1, 2, now you add upon third generator. Now total cost is the cost associated with the generation 3, F3 of P3, and total demand minus P3, that means is equal to P1 plus P2 ultimately. So you have from the previous table, you have the best combination of 1 and 2, right? Like how we did solve for the ventures investment, you have the best combination of 1 and 2. Now you are just bringing in generator 3 also. The same approach you need to follow, there is no difference. The same approach you follow. Let us take one example to understand. Now let us say you have let's take any number. Let's say you have 275 megawatt of load demand to cater. Now by taking 50 megawatt of generation from generator 3, what you get? $806 per hour. And if you take 50 megawatt and 275 megawatt of load demand, the remaining 225 need to be catered by the best combination of generator 1 and generator 2, right? Now 275 megawatt minus how much? 50 is 225. Now what is the best combination that it is clearly indicating from this table? This is $311.5 per hour. So 311.5 plus 806 will give you 3921. Similarly you do it for all the generations. Well, generation is increased from 50 megawatt to 175 megawatt. You have to kindly note this point, because each generator has its own limits. How that limit you are obtaining is because of the demand which is fixed from within the range of 300 to 325, right? Now it's just as it is. Now you get the best combination of generators, best combination of generation from generator 3 at this stage, right? Now ultimately you are interested in you are interested in these 2 entries only, because ultimately your concentration is 300 and 325. Between this you need to find out 310. So I am just asking you to summarize that in a table. So for 300 megawatt you have the best combination from the previous table, 4035 4377.5, and you have the entries at different levels, right, of generations. So you get F3 as 4168. You see here F3 as 4168, and then P3 as 150 megawatt. This is the best combination for 300 megawatt of generation. For 325 you have F2 of double D. F2 of double D is the best combination of generator 1 and generator 2, that is 4377.5, and the best combination of generator 3 is again 150 megawatt, but that is coming out to be 4463, right. Now you see here, finally you get the list for 300 megawatt of generation, 300 megawatt of load demand. The cost associated is 4168, right, and the combination is P3 is 150 megawatt, because now you get for 300 megawatt of generation from the previous table, what is the best generation? 150 megawatt, and you should check if you subtract 150 from 300, what is the remaining? You get 150 megawatt. So you should check for the best combination of generator 1 and 2 with respect to 150 megawatt of generation, right. So that for 150 megawatt of generation you freeze P2 as 100, right. So the remaining will be scattered by generator 1. That means ultimately you get P3 as 150, P2 as 100, and remaining as P1. Similarly you get for 325 megawatt. So this is the entry you get. Now ultimately your generation is, the P1 is already fixed, which is 50 megawatt, correct, and P3 is also already fixed, which is 150 megawatt, which is not varying. The only variable which is varying is generator 2, that is from 100 to 125. That means you can consider this generator to operate as it is supposed to vary from 100 to 125, and that's what it is indicating. By varying from 100 to 125, it is giving the best possible solution. Now you, rather than operating at 125, you operate from 100 to 110, that's it, because your load demand is not 325, it's just 310 megawatt. So for the 310 megawatt, okay, for generator 2 you have to interpolate, that's it. For 100 megawatt of generation you have a specific cost for generator 2, for 150 you have another, for 125 you have another cost. So you just have to interpolate what is the cost, tentative cost, that is 1478. So you have total cost of generator 1 for 50 megawatt, which is 810, for generator 3 which is operating at 150 megawatt, you have this cost. So you just have to add these three to get the total cost of operation, which is $4286 per hour. For this specific load, the combination of generator 1, 2 and 3 will give you the best cost, which is $4286 per hour. I hope this is clear to you. So that's it for today. Thank you very much.